So I want to go over the example in the text. And we were studying the function f of x is x plus 1 squared over 1 plus x squared. And we're going to study this function using the techniques that we've picked up we'll get to see how it behaves, also get a sense of how to graph it. And there's basically a 7-step process that the text recommends. Now, the first thing we want to look at, domain, or where along the x-axis this function exists. And then symmetry. Now, symmetry helps us to graph this thing. It gives us an idea. For example, if we have a function and we graph this much of it, and we know it's symmetric across the y-axis, that means it's a mirror reflection of itself across the y-axis, well then we could just do that and we're done. But let's take a look at domain. So first off with domain, we're looking for places where this function might not exist. And these are basically places along the x-axis or values of x. And things that could get us into trouble are like square roots, tangent functions, secant functions, natural log functions, functions where there are certain x values you can't put in there. But if we take a look at this, we don't see any square roots. There's no tangents or secants. No natural logs. So those aren't going to create an issue for us. Also, there are no restrictions. Oftentimes, if you're working with functions involving time, you'll see a restriction like time has to always be greater or equal to 0. But we don't have any restrictions on x that are like that. Another thing to keep in mind is the potential for division by 0. And there actually isn't. Now, if we take a look at this denominator, 1 plus x squared, this can never equal 0. And the reason is x squared is never negative. And since it's never negative, it can never be -1. Now, this is true for real numbers. So we're not going to worry about imaginary or complex numbers. So this denominator will never become 0. This would have to be -1, and then -1 plus 1 would be 0. But there's no real number that you can square that becomes negative. Only complex numbers or imaginary numbers is that the case. So what this says at the end of the day, the domain is negative infinity, infinity. Now, the next thing we're going to look at is symmetry. And again, this helps us graph the function. Now, we have 2 types of symmetry that we look for. There's y-axis symmetry, where the function is going to be a mirror reflection of itself across the y-axis. And this says that if we take -x and we put it into function f, well, it simplifies down just to the original function again. Or put another way, if xy is on our curve or our graph, then so is negative xy. That will also be on our graph. So that's one kind of symmetry. The second kind that we look for is about the origin. And we know we have this if when we put in negative x, we simplify, the negative sign simplifies out. Or put another way, if xy is on the curve or our graph, then so is negative x, negative y. And a function that looks like something that's symmetric about the origin if you take the function y equals x to the 1/3, that looks like something that's symmetric across the origin. All right. So let's test the symmetry of this function. So let's plug in negative x into f. Well, we'll get this. And it's just going to simplify down to this. So what does this tell us? Well, first off, the original function, f of x. If we plug in negative x and we just get f of x, when we simplify, and this is what we get when we simplify, well, then this is symmetric across the y-axis. But if we look at f of x, this is f of x, this is f of negative x, and they don't look the same, and they aren't. So this is not the same as this. So that means f of x does not equal our f of negative x. So f of x does not equal f of negative x. So that means we don't have symmetry about the y-axis. Now, the other possible outcome is we could get negative f of x. We put in negative x and we get this. That means they're symmetric about the origin. But this also is not equal to the f of negative x that we got after simplifying. And again, this is f of negative x. Excuse me. So that means f of negative x does not equal negative f of x. So that means we're not symmetric about the origin. So it turns out this function, no symmetries. So we're not going to have symmetry across the origin. We don't have symmetry across the y-axis. but we do have a domain that's everywhere. Or at least we don't have any evidence of symmetry. So for step 2, we're going to look at the derivatives, or at least we're going to compute them. And if we compute them, we would use the quotient rule, or you could use sort of a fancy version of the product rule. Get a little creative with that. But typically you would use your quotient rule. That'll be our first derivative. Excuse me. And this will be your second derivative. And again, you take the, let me double check my number here. You would take the derivative of the first derivative to get your second derivative. I'm going to double check my notes. Now, what are we going to do with these? Well, we've already studied the function. There's more we can study with this. We'll get to that later, like intercepts, for example, y-intercept, x-intercept. We're going to ask a question whether this crosses a horizontal asymptote or not. There's more we can do with this. This is a lot of what we did in college algebra. The first derivative, we're going to study critical points and also increasing and decreasing. That's what we'll use this first derivative for. For the second derivative, we're going to look at concavity and inflection points. So now we've got these derivatives. Let's start using them. This will be our third step. We're going to start looking at critical points. And we're going to use the second derivative also for this purpose. So you use the first derivative to get critical points to begin with. First derivative will give you critical points. The second derivative will give you the inflection points. But we use both the derivatives, first and second. We can use them both to study what's going on with these critical points. So for critical points, this is where f prime of x is 0, or f prime of x is undefined. So let's take a look at our derivative here. Now, is there any place where this could be undefined? Well, again, there's no square roots or even roots. There are no tangents or logarithms or secants or things like this. So those aren't going to be an issue. Now, is there a possibility of division by 0? Well, we've got the same situation as before. Whatever x is, this only becomes 0 if x squared is -1. But there's no real number that we can square that would give us -1. So that means this will never become 0. So there is nothing, no value of x that makes this undefined. So what we can look for instead is where this equals 0. And we can multiply both sides. 1 plus x squared squared. Those will cancel. We can divide by 2. And we can add our x squared to both sides. And so we get 1 equals x squared. Square root both sides, we'll get plus or minus 1 equals x. So that's the critical points for this function. X is 1 or x is negative 1. So what do critical points mean? Well, recall that the derivative of a function is the slope of a tangent line to f of x at x. So here's our f of x. Here's some value x here. And then there's a line that's tangent. That means it contacts f of x at one point. And the slope, what the derivative is the slope of this tangent line. So if this tangent line has an equation, y equals mx plus b, the slope of this tangent line will be the derivative of x, or derivative of f of x. So what are we doing when we set the derivative equal to 0? What's going on here? Well, when the derivative is 0, the tangent line is, put another way, has a slope of 0. Or if we think about lines that have a slope of 0, you can recall from algebra, a line with a slope of 0 is a horizontal line. It's a perfectly flat line. The line is horizontal. Excuse me. So when we have horizontal lines, we could have a situation like this, where we have a peak in our function. Here's f of x. And here's the tangent line that's perfectly perfectly flat. They tell us where there might be peaks, or they could tell us the bottom of troughs. Again, here's another horizontal flat tangent line. And then sometimes they don't really tell us either of those things. We could get something kind of like this. Where it's neither a peak or a trough. It's just sort of a landing, and then the function keeps going up. Now, what we're interested in with these critical points is if we're dealing with situations like this and this. And this is what's called the first derivative test. We're looking for what's called a local max or a local peak or a local minimum or the bottom of a local trough. So this is where the first derivative test comes in. So let's say we have a situation like this. There's f of x. And let's say we discovered a critical point, C, like the -1 or the 1 that we just discovered, because we set the derivative equal to 0, we solved for x, and we found that x was -1 or 1. So this could be like -1 or 1 here. Well, at this point, we could have the bottom of a trough. But then let's say, I'll make this a little less long, need some room. We take a look at some other tangent lines. Here, let me draw this a little more clear so the tangents stick out a little bit better. Move my C here. So here's where our tangent has a slope of 0. But let's say if we look at the tangent lines after and before, well, here we have a slope of 0, but after this, the derivative will be positive because the slope of the tangent lines they're going to also be positive. And then on this side, the slope of the tangent lines are negative. So using the first derivative test, when we see that we have negative slopes, then a 0 slope, and then positive slopes, or put another way, negative first derivative, 0 first derivative, positive first derivative, this means we have a local minimum. Now, we could have the other situation that we're looking for. Now in this situation, we still have 0 at our critical point. Excuse me. Now, then after the critical point, we're going to start seeing tangent points or tangents that have negative slopes. But before the critical point, we have tangents that have positive slopes. Or put another way, the first derivative is positive, then it's 0, and then it's negative. And this tells us we have a local max. So what are we going to do? Well, we've already set f prime of x equal to 0. And we solve for x. So we just did this. In solving for x, we found out that the first derivative is 0 when x is -1 and 1. So this is what we found out so far. We found critical point at -1 and a critical point at 1. Excuse me. So now I need to figure out what's the value of f prime of x, or what's the value of the tangent slopes before we get to -1, between -1 and 1, and then after 1. Now, these are the only locations where the first derivative is 0. So what that means is that a function can change sign either when it encounters a vertical asymptote, or if you have some kind of a, say, a piecewise function, which we don't have either for f prime of x. F prime of x does not have a vertical asymptote, and it's not a piecewise function. It's a continuous function. It's a smooth function. So since it's continuous, it only changes sign when it becomes 0. So that means f prime of x will only go from negative to positive, or positive negative, when it becomes 0. So that means f prime of x will only change sign here or here. It won't do so. It will not change sign anywhere out here or in the middle. Because f prime of x is continuous, that means it's a smooth function with no sudden jumps or gaps. It'll only go from positive to negative or negative to positive here or here. So that means if we find the sign of f prime of x at one point, we can assume that will be the sign of f prime of x for all the points in this part. Same thing here, just need 1 point. Same thing here, just need 1 point. Just going to sample. So I recommend using numbers that are fairly easy to compute, relatively easy to compute. So let's try these. Let me just check a little calculation here. Let's see. All right. So let's take a look. F prime of -10. If we plug -10 in for x, and I'll just give you the computation I came up with. The key thing, it's going to be negative. So what that's going to mean Let me just double check just want to make sure I'm not making any arithmetic mistakes. All right. So this came out negative. So what that means, because f prime of x can only change sign at this 0, if it's negative here, it's going to be negative everywhere. Well, I'll save this for another graph. Now, f prime of 0, we calculate that, we'll get a positive 2. So that means everything in here is positive. All the tangents are going to have positive slopes. And then finally, f prime of 10, well, we're going to get this number again. And of course, it's negative. So what this tells us here, I better redraw this. Need a little more room. We had 0 and 0. This is negative because f of negative 10 was negative. This is positive because f of 0 was positive. And this one here, f of 10, that was negative. So this is all going to be negative. So now we can use that first derivative test. Now the first derivative test says when you have negative slopes, 0 slope, and then positive slope, that means this critical point is a local min. And then when you have positive then negative with 0 for your critical point, that means you have a local max. So it looks like we have a minimum, some local minimum here and a local max here. Now, this is one way we can learn about the behavior of what the function is doing at these critical points. This is one way of doing it. There is another way. The other way is the second derivative test. And we're going to bring in our second derivative. Which is this. Now, specifically, we're going to be looking at concavity. And when we see something like this, we say this is concave down. And that's going to be suggesting that there's some kind of a max possibly here, possibly. Or we have concave up. So the way this works is this. We're going to still work with critical points. So we're still dealing with the situation where, let's say we have this. So again, this could be that -1 or 1. That's what C could be. So for the second derivative test, what it says, if we find a critical point, f prime of C, where it's equal to 0, and if the second derivative of C is positive, then what this says is that we have concave up, and there's a local min at x equals C, our critical point. So this means that we can use the second derivative instead of test points with the first derivative to determine if we have a local max or a local min at C. Now let's say we have this situation. Again, C is a critical point. So that means f prime of C is equal to 0. But if the second derivative at this critical point is negative, then we have concave down, and that means we have a local max at x equals C. So what we're doing is redundant. What this is definitely redundant. We're going to figure out what we already know using the first derivative test. We're just doing it using the second derivative test. So this is another way of figuring out whether those critical points that we found using the first derivative, whether those are local minimums or local maximums. And this one thing to mention with the second derivative test, if f double prime of C equals 0, the test fails. And when it fails, you could have a minimum, a maximum. You'll have to verify this, or neither. You might have neither, but you have to verify this some other way. All right. Now there is a special point, though, where the second derivative equals 0. We're going to talk about that later. But for determining whether a critical point is a min or a max, the double prime, f double prime at the critical point being 0, it won't tell us if we have a min or a max. But there is another special thing when the double derivative is equal to 0. We'll talk about that later. So again, we're just going to verify what we already know, what we found with the first derivative test. So our critical points are -1 and 1. So f double prime of -1, this turns out to be, let's see, and let's see here, we'll get -4 times 1 minus 3 is -2. over 2 cubed. And this will turn out to be positive 1. So this is positive. So that's going to mean concave up or a local minimum. Now, f double prime of 1 and we'll get 4 times negative 2 over 2 cubed, which is negative 1, which is negative. So this means we have concave down because the second derivative is negative. And this means a local max. So again, we're just confirming what we already know with the first derivative test. This is just another way of doing it. Now, the next thing, step 4 in this process. So we studied what's going on at the critical points, and whether we use the first derivative test or the second derivative test, we figure out that at those critical points, negative 1 and 1, we have local min at negative 1 and a local max at 1. So now we're just going to study increasing and decreasing. So for this, we're just going to bring back that little graph that we already had of the first derivative. And we know it's 0 at negative 1 and 1. It was negative here, positive here, and then negative again. Now, where the first derivative is negative, this is where the tangent lines to the function have a negative slope. Or you could think of it as like where the function has a negative slope. But technically, it's the tangent lines to the function have a negative slope. That means we're decreasing. Where the tangent lines have a positive slope, increasing. And where they have a negative slope again, it's decreasing. So we can try to imagine what this looks like. And this is where the derivatives can be powerful. If we don't know anything about the function, if we just have its derivative and nothing else, we weren't given the function originally, well, we can use these little pictures of tangent lines. These are flat horizontal tangent lines when the slope is 0. And then here they're going to be decreasing. Here they're going to be increasing. So I better put a flat one up here. And then here they're going to be decreasing again. So very roughly, and here's up, I'll kind of emphasize the 0 slope ones. But we seem to be doing something like this. Our graph seems to be behaving sort of like this, looking at just the first derivative. So for decreasing, from negative infinity to -1, not equal to -1, it's 0 at -1. We could union that with 1 to infinity. And it's increasing from -1 to 1. So that can help us get a picture of what's going on. All right. So next what we're going to look at, let's look at inflection points and concavity. So these are just different ways, and some of these techniques, again, they're going to be a little redundant. You're going to say, well, I can kind of see what's going on. I might not need to do all this work. Fair enough. But these are just sort of different ways of looking at this function, seeing what it's doing. And this one's got some interesting properties. So let's recall concave down. Concave down is when the second derivative is negative. And concave up is when the second derivative is positive. So in this case, well, maybe not in this case, but sometimes we'll get a function like this. And when we do, this part would be concave down. And this part is concave up. But there's a special point where we transition from concave down to concave up. And this is what is called an inflection point. So this is something on our graph we might be interested in, another one of those interesting properties where we transition from one concavity to the other. And where do we find inflection points? This is where the second derivative of f of x being 0 is important. When that second derivative is 0, that's where we find these inflection points or these transitions, that transition point from one concavity to the other. So let's look for those transition points in this function. Let's take a gander. So our second derivative is 4x, x squared minus 3, over 1 plus x squared cubed. So we're going to set this equal to 0. So solving for x, we'll multiply both sides. And so we'll get 4x, x squared minus 3 is equal to 0. Now this can be 0 when with two situations here. We can use our zero product property when this is 0, or if this is 0, we get 0. So first off, if 4x is 0, well, we just find out, we divide by 4, we get x is equal to 0. And when this is equal to 0, square root both sides, get x is plus or minus square root of 3. So the second derivative is 0 when three things are going to happen. When x is 0, or x is plus or minus square root 3. Now, another possibility for the location of an inflection point, again, is when f double prime x is undefined. That's another possibility. It's not only just where f double prime of x is 0, it's also when it's undefined. Again, if we look at this, there's no square roots, no tangents, no secants, no natural logs. And again, this 1 plus x squared will never become a 0. So this is going to be defined for all values of x. So that means the only points that are going to be inflection points are where we have this equal to 0, or this is equal to 0. And when we solve for x, we'll get x is 0, or x is plus or minus square root 3. And these are the places where the concavity changes. So let's study the concavity. Now we're going to do the same thing as before with the first derivative as with the second. So instead of looking at the values of the first derivative, we're going to look at the values of the second derivative. Now it's 0 at negative square root 3, 0 in square root 3. So this is where we're going to see a transition from concave up to concave down, or concave down to concave up. We're going to see that transition at these points. Now, these are the only locations where the second derivative is equal to 0. And the second derivative was also a continuous function. There were no places for vertical asymptotes like divisions by 0. This was not a piecewise function. There's not going to be any jumps or gaps. So that means this is a smooth curve. What that says is this will only change sign when it becomes 0. So if it wants to go from positive to negative, it has to become 0 first. Well, it only becomes 0 at these three locations. So that means only at these three locations can f double prime of x change sign. So what that says, if it's negative at one point here, it has to be negative all through here. If it's a positive at one point here, it'll be positive all through here. Same here, same here. So we're going to use test points again. And again, I recommend using fairly easy points. So let's test f prime of -10. Now, if we plug in -10 into our second derivative, we're going to get this. But the key thing here, it's negative. Now, if we do f prime of -1, we're going to get a +1. I'm sorry, f double prime. F double prime of 1, we'll get a -1. And then f double prime of 10, we're going to get a positive fraction. So what is this going to tell us? Well, what we're going to do is we're looking for concavities where the second derivative is 0, or where it was undefined. And in this case, we don't have any x values that make it undefined. So just using x values with 0, those are going to be transition points from one kind of concavity to another. So you have 0, 0, and 0. So -10 was negative. So that means the entire second derivative is going to be negative along that. F of -1 was positive, so we're going to get this. F of 1 was negative. F of 10 is positive. So if there are concavity changes, they're going to be occurring at these inflection points. And sure enough, that's what we're going to see. So when the second derivative is negative, that's concave down. When it's positive, it's concave up. When the second derivative is negative, concave down. And when it's positive, concave up. And we're going to see these transitions in concavity at -√3, 0, √3. Now, this sort of seems to suggest we're going to see something kind of like this. But not necessarily in this manner. And when we graph our function, you're going to see it's a very interesting function, the way it actually does behave in the end. But it looks like we could be dealing something like this, just looking at concavity. But we're going to need more information to get the full picture. So just to summarize what we have for concave down, we have this from -∞ to -√3, and also on 0 to √3. For concave up, negative square root 3 to 0, square root 3 to infinity. All right. So let's take a look. The next thing they're going to have us do are the asymptotes. Now, if we take a look at our function, there's no division by zeros here, so there's not going to be any vertical asymptotes. Because if you think about like vertical asymptotes, for example, I'm just going to give an illustration. If we had, say, g of x is 1 over x minus 1. Well, you get a vertical asymptote at x equals 1. So your graph does something like this. And you're getting this vertical asymptote where the denominator becomes 0. X equals 1, 1 minus 1 is 0. And so if you get this vertical asymptote at x equals 1. In this case, again, we can't get a division by 0 because this will always be positive and it needs to be negative to cancel that 1. So no vertical asymptotes. Now, what about horizontal asymptotes? Well, we can do those, and there's a couple ways we can do it. I'm going to go through both methods. It's kind of a review, but we'll do the algebra way and we'll do the calculus way. So this is for horizontal asymptotes. I'll abbreviate this as HA. So we take our function. We're going to expand this out. We'll get x squared plus 2x plus 1 over 1 plus x squared. So I'm going to do this the algebra way. And this is where you have to bring back those long division skills for polynomial division. So we're going to divide this by that. So x squared, we need to have an x term. This is one of those things you have to do with this long polynomial division. So you have a 0x term. And then we divide it. X squared plus 2x plus 1. So this is sort of a blast from the past, as they say. So do polynomial division. We divide this into the first term. X squared divided by x squared is equal to 1. Put a 1 over the constant section there. Then we take this, we multiply it to the whole thing. And when we do that, we'll get x squared plus 0x plus 1, because we're just multiplying by 1. We subtract, we'll get 2x. And that's it. That's going to be our remainder. So the answer is 1 plus 2x over this. I'm going to leave out the 0x. I'm just going to say x squared plus 1, because 0 times x is just 0. And so that's what we end up getting. So what we did in algebra, interestingly enough, was basically take a limit. So our f of x, we can rewrite it That's all that this does. We get to rewrite it like this. So what we did in algebra is we really kind of used some imagination. We would say, well, as x gets bigger and bigger, like if it becomes 100 and then 1,000 and then 10,000, 10,000 squared is much bigger than just 10,000. So as x goes to positive infinity, then 1 plus 2x over x squared, this becomes practically 0 or 1. And then as x goes to negative infinity, again, like negative 10,000 squared is the same as 10,000 squared. And then this is going to be negative 10,000, but negative 10,000 divided by 10,000 squared, again, that's going to be a really tiny negative number. So using our imagination, this is going to go to 1 plus 0, which for all intents and purposes is 1. And you can experiment with this, like try using x being 1,000,000, negative 1,000,000, and you're going to find it's going to be 1 plus a small number. Try 1,000,000,000 then, negative 1,000,000,000 and 1,000,000,000. It's going to be 1 plus an even smaller number. So what this says is that the horizontal asymptote, in other words, as you go farther and farther down the x-axis, this function becomes practically 1. So this function, which is equal to this, as you go farther down the x-axis, this becomes practically 0. And so this function f of x, though it looks pretty complicated, it'll sort of settle down to be close to y equals 1, because this term basically disappears. So that's how we handled it in algebra. Now, the other method we can use is now from calculus. A little more, I guess you could say a little more precise. So again, we take f of x. I don't know about precise is the right word. But it is a method that we're familiar with, and you might feel more comfortable with it, I think I should say, because other than that discovery of the horizontal asymptote, we don't do too much with infinity in algebra. In calculus, we do. So maybe the correct phrase is something that's maybe a little more comfortable working with. So what we're going to want is this. To find the horizontal asymptote, we want the limit at it as x goes to the infinities, I'll say plus and minus infinity of f of x. That's how we're going to find a horizontal asymptote. So let's start with the plus infinity. And then we're going to be doing this. This is our f of x expanded. And we're going to use that technique where we multiply top and bottom by, or we divide top and bottom by x squared. So we'll get the limit as x approaches positive infinity of x squared over x squared plus 2x. And we're dividing the entire top by x squared, the entire bottom by x squared. So we get the limit as x goes to positive infinity of 1 plus 2 over x plus 1 over x squared over 1 over x squared plus 1. And if you recall, the limit of 1 over x squared when x is going to infinity, this is 0, 0. And then a constant over x as x goes to infinity is also 0. 1 plus 0 plus 0 over 0 plus 1. Well, that's 1 over 1. And we get the same result as we did using algebra. If we think about x becoming bigger and bigger as x travels down the positive x-axis. And then we'll use the same trick. If you use the exact same trick as x goes to negative infinity, again, we'll divide the entire denominator by x squared, entire numerator by x squared. I'm going to skip a step here. I'm just going to kind of cut to it. You get x is negative infinity. You'll get 1 plus 2 over x plus 1 over x squared. And then 1 over x squared plus 1. You're going to get the exact same thing. As x goes to negative infinity, this will be 0, 0, and 0. And then once again, oh, you'll get 1. So once again, the horizontal asymptote is going to be y equals 1. Now, there's a question we want to ask about horizontal asymptotes. And it's going to be this. Does f of x ever cross the horizontal asymptote y equals 1? Now, for vertical asymptotes, this isn't an issue. Vertical asymptotes, those don't get crossed. But horizontal asymptotes, those do get crossed. Now, how often they cross, who knows? What the horizontal asymptote tells you what's going on. Like the function, like let's say we have our rectangular grid. Say this is the horizontal asymptote. Our function could be doing all kinds of strange things, but then as x goes out to positive infinity, the function settles upon the horizontal asymptote. Same thing as it goes to negative infinity. So that's what the horizontal asymptote tells us. It's about the behavior of the function, as you go far down the positive x-axis or far down the negative x-axis. It's the vertical asymptotes that you don't cross. Those are sort of the places where the function can't go because it's not defined there. So horizontal asymptotes tell us about behavior of the function. So it is possible for the function to cross them. So to find out where that is, we take our function f of x. And we set it equal to that horizontal asymptote. So multiply both sides by 1 plus x squared. One times 1 plus x squared is just 1 plus x squared. And then if you want, you could expand this. I'll put this in descending order. Subtract from both sides, the x squareds cancel out. Subtract from both sides, the ones will cancel out. You're going to be left with 2x is equal to 0. These will cancel. The ones will cancel. So you just get 2x is equal to 0. Divide both sides by 2. We get x equals 0. So what does this say? F of x crosses the horizontal asymptote y equals 1 at only one location, at 0. Oh, let's find out. It's going to be 0, 1. And if you're not sure about that, you can just plug in 0 into f of x. But remember, the horizontal asymptote always has a y value of 1. But it crosses at 0, 1. So if you just wanted to go through the motions and check it, go ahead. That's what you should get. So that's going to be a special point. We know we cross the horizontal asymptote at 0, 1. This is also, if you notice, a y-intercept. So we cross the horizontal asymptote at a y-intercept of 0 and 1. So this brings us to the discussion of special points. This is sort of the last thing we're going to do to study this function before we graph it. So special points. So let's find out. We know that we cross the horizontal asymptote at 0, 1. Let's find the exact location of the critical points. We know the location along the x-axis. Let's actually make these points that we can plot. So they're at -1 and 1. F of -1 is going to turn out to be 0. And f of 1 is going to be 2. So that means our critical points, -1 and 0, 1 and 2. For the x-intercept, we said f of x equal to 0. We solve for x. Multiply both sides by 1 plus x squared. So it'll cancel on this side, it'll be zeroed out on that side. Square root both sides. Plus or minus 0 is just 0. Subtract 1 from both sides. X is minus 1. So this means the x-intercept is -1 and 0. So finally, the y-intercept, and we actually already have this, but if you didn't notice, you're like, oh, yeah, that's right. Well, let's say you didn't notice it. Well, for the y-intercept, what we do, let this be our function. Let x be 0. So to find an x-intercept, we let y be 0. To find the y-intercept, we let x be 0. And what you'll get when you simplify is 1 over 1 or 1. So 0, 1, which again turned out to be the same point where we crossed the horizontal asymptote. So finally, we're going to try to draw this thing. We have a whole bunch of data. We know about its concavity, where it's concave up, concave down. We know where it transitions in concavity. We know where we have critical points that have local maxima, local minima. We know intercepts. We have a horizontal asymptote. Let's make sure. Now, square root 3, it's about 1.7. So it's about there. Negative square root 3, negative 1.7, about right there. Let's put in that horizontal asymptote. Now, the y-intercept is 0, 1. It's also the same point where we cross the horizontal asymptote. So that's a point on our graph. We also had an x-intercept at negative 1 and 0. Now, what we also know is this, though. Now, the critical point, one of the critical points that we have, let me go back here. I should probably list these points out. So let me put these so we can see them. So the horizontal asymptote cross was 0, 1. The y-intercept was also 0, 1. The x-intercept, negative 1, 0. But one of our critical points, I'll call it C1, was also negative 1, 0. And then a second critical point, I'll call it C2, was 1, 2. So it was up here. Now, what we learned about C1, whether we learned it from concavity with the second derivative test, or we learned using the first derivative test, This is a local minimum. And then C2, again, using the first derivative test or the second derivative test with concavity, this is a local max. Right here, I put it here so it's easier to see. Now, let's talk about the first derivative test. The first derivative test says that the function is always decreasing to the left of -1. So that means the function is doing something like this. And then it hits a bottom here at -1, because -1 is a local min. But then after -1, we find that the function is increasing from -1 to 1. So it's doing something kind of like this. But then at 1, it starts decreasing. Now we know that it only crosses the horizontal asymptote at this point. It won't cross here, and it won't cross here. So the function's doing something sort of like this, where it's getting close to that asymptote, but not gonna quite cross it. And again, this is from that first derivative test, and I'll put the results for that up here. Well, not so much the first derivative test, I should say. You could also say it's the study of increasing and decreasing, where we're decreasing, increasing, and then decreasing. Now, another thing to keep in mind, we can adjust our graph a little bit, is concavity. We know that there's transition points at these locations for concavity. And if we think about our concavity, what we're going to have, we'll put in F double prime. We had a 0 at -√3, a 0 at 0, and a 0 at √3. Now the second derivative, we had negative, 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 0, positive, 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 0, negative, 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 and positive, 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 positive. So what it says is from -infinity to 0, this is concave down. So that means we're doing something like this, but then it's going to be concave up. So then we're going to do something kind of like this. And this will be a transition point from concave down to, oh, so slightly looking concave up. It's going to stay, oh, so slightly concave up, and then it's going to transition the concave down. So this lets us sort of finesse a little bit, or maybe not finesse, but fine tune the appearance of our graph. So it's going to be concave down again. And then here, the second derivative is positive. It's going to be concave up again. It's going to get ever so closer to that asymptote. So using the first derivative, we can see that this is always going to be decreasing, that the tangent slopes are always going to be negative. But then starting here, the tangent slopes are always going to be positive. And then here, the tangent slopes are always going to be negative, however slight they might be. Using the second derivative, we should have sort of a turned over bowl shape, then transitions to a right side up bowl shape. And it stays that way. And then here you get a transition to a turned over bowl shape. And then here it transitions to a turned upright bowl shape. Then we have where we contact the x-axis and the y-axis as well as the horizontal asymptote. And then we also have here where we have a critical point max and a critical point minimum. And since this is always decreasing forever, it's never going to suddenly pop back up and then come back down. So that means this is not just a local max, it's going to be an absolute max. And then here, it decreases here and then stops. Then it's increasing, or I'm sorry, not increasing, but if you look, the first derivatives tell us this is always going to have a negative first derivative. So it's always going to be doing this. It's not going to suddenly become positive like this. It's not going to have a positive derivative and it does something else. For example, you're not going to see something like this. So roughly our graph is sort of looking like this. And it's never going to go beyond. It only crosses that horizontal asymptote at this point. And it's always going to be slightly getting closer, where the tangent lines are always going to be slightly negative on this side. It's never going to do something like this. And the reason it won't, and this is how we know this is going to be an absolute minimum, is that it would have to have a dip like this. That only happens if you have a positive tangent slope, then a 0, and then negative. These are the only zeros. And according to our first derivative, the tangent slopes are always going to be slightly decreasing like that. So what we can get from this, not only is this a local min or max, it's an absolute max. And this is also an absolute minimum. And again, the reason is, for something to be lower than this, you'd have to have a dip like that, and you would have to have a positive first derivative in order to pull that off. And this says the derivative will always be negative. It's always going to be coming down like this. It's never ever going to be coming up like this. Because this is negative, it's always dropping down. The only way you can get a lower point is if you come up from a bigger depth. But you can't be coming up if your first derivative is negative. You can't be doing this. This you can't do. You're always doing this, according to what's going on here. So that's it. I hope that helps. If any questions, let me know. But that's how we can use derivatives and second derivatives to help us graph our functions and learn about their behaviors. So other than that, let me know if you have any questions, and have a wonderful weekend.